All right, so let me repeat this. The test will be due Thursday at 11:59. It's open book, open notes, use the internet. You will be graded mostly on your ability and clarity to provide detail to solutions. The only rule that I will ask you is to not discuss the problems with another human being. And it will be ready for you no later than 8 a.m. tomorrow. So, does anybody have a question about the exam? Going once? So there we go. I love a good question. That was my next thing, Heather. So the question is what sections will this cover? So sounds silly to say this, but I'm going to say it. Essentially, it covers K, that's kindergarten, or whatever you learned at home, through section 3.3. That's what it will cover. Now, I'm joking, obviously, about this kindergarten business, but it's really not a joke, because if you can't do the mathematics that you learned as a child, then you can't do the mathematics that you learn in middle school and high school. And if you can't do the mathematics of middle school and high school, it's really difficult to do university level math. So I'm being funny here, but you need to understand how to do arithmetic, and you need to understand elementary geometry, and you need to understand algebra. And then if you understand that, then you're able to do the problems in this book. So if that's how you want to keep score, you are going to be required to do problems up through section 3.3. Does anybody have a question about this? Comment. All right. Very good. Okay, so I posted a homework yesterday, and we're going to do some of these problems together right now. But even when we do them, or you go on the internet and find solutions, it's extremely important that you learn these derivations on your own. I mean, if you want to get anything out of this course, you got to be able to do the problems. So I hope that you really take the time to learn these sort of calculations / derivations. So let's sort of get back into it. Right now. So we had a huge definition at the end of last class. So so we took a very specific limit and we gave it a name. So basically, we're saying if you have a function, and if we study a specific limit associated with this function, then this limit, when it exists, gives way to a new function, which is extremely useful. And since it's extremely useful, we give it a name. and it's called the derivative. So what is this? Well, the notation we used is we used f prime of x, and how is it defined? It's defined as this limit. So you recall we spent a lot of time earlier in the semester talking about this thing on the right, which is called a difference quotient, and why this difference quotient had two very useful interpretations. I mean, there's more than two, but right now we know of two. That is that we can think of a geometric interpretation in the terms of what's called a tangent line, or we can think of a physical interpretation. Whereas if this function tells us our displacement or maybe our distance traveled, then this limit gives us a means for defining velocity. So it's very important that you understand that this thing in this red box that I'm about to draw, this is a definition. We are defining something. So one of the things that I'd really encourage that you strive to understand is that in mathematics and in other branches of science, there is a difference. You must be able to distinguish between what we call a definition and what we call a theorem, because they're two different things. So one of the things that most of you students will learn is that, and some of you already know this, is that many definitions in calculus are very complicated. This is a complicated definition. However, from these complicated definitions, we can deduce logically shortcuts. Now, these shortcuts, technically speaking, are called theorems. They are results that allow us to take hard computations and do these hard computations in a very quick and efficient manner. However, we are learning calculus, which means you not only have to understand the easy shortcuts that we're going to talk about, but you also have to understand the actual definitions. Okay. That being said, does anybody have a question or a comment before we move on? Okay, so let's do an example. Actually, before that, so we also discuss notation. So for example, f prime of x df dx, and say d dx of f of x. These are three ways to write the same thing. And so depending on what we're working on, we might choose one of these three notations just because it's cleaner. So let's do that. Let's do some examples. and we'll use all these different notations. So the first example we'll do is we'll take a very simple function. So this is what we like to do in science. We like to start with the simplest things, and then hopefully we build our way to the more complicated things. So in mathematics, there's no simpler function than the function that spits out the same number at every point. These are what we call constant functions. And a constant function is also what we associate with a horizontal line if we want to think of it as a geometric entity. So if I take, for example, f of x equals 4, what is the derivative? What is the derivative of this function? Now, before we do any computation, it's worth thinking about what we expect this to be. So if you get in your time machine and you go all the way back to like our first and second lecture, we talked about that we had some goals in this class. One of the goals of this class was to define velocity or rate of change. And what we did is we looked at curves and we said, okay, we need to understand that there's got to be a way that we talk about how steep a curve is. And then we said what we'll use there is we'll use the idea that if we have a line, we already understand how to discuss the steepness of a line. You have this thing called slope. That is a way of us quantifying how steep a line is. And so what we thought is if we use this idea to generalize the concept for general curves. Now, you guys learned in algebra class that the slope of a horizontal line is 0. So we should expect then that if we are going to compute the derivative of a horizontal line, a constant function, we would expect then that the derivative, if its job is to measure rate of change, well, there is no change on a horizontal line. As you move left to right, it doesn't go up or down. It stays the same height. So we expect this derivative to be 0. So let's work through it and let's see if that's what we indeed get. So if I take f prime of x, we know by definition it's this. Now, I know that for each input, my function always spits out 4. That's what it does. So what I get here is 4, and then I get here I have 4. So I get 4 minus 4 over h, which simplifies to 0 over h. And then 0 divided by h is 0, and so of course this limit is 0. And so we can conclude that the derivative of the function 4, or y equals 4, is just 0. Now, there's a couple things to be said about this, and before we do that, I'll let you think about if you want to ask anything. All right, any questions, comments? What's interesting about this, and we'll come back to this in a second, is there's really nothing special about 4. If the function was f of x equals 26, you'd get the same result. If the function was f of x equals -10, you would get the same result. And if you think about the geometric intuition, you should be okay with that, because you are like, oh, okay, I get it. Constant functions have graphs that are horizontal lines, and there is no change in a horizontal line. Its slope is 0. All right, so let's do another example. So we're going to write it a little differently here. Let's now write it like this. We'll use this notation. I want to know what the derivative of 5x minus 1 is. Now, if you use your geometric intuition, you'll say, okay, the function we're trying to differentiate is a line that has slope 5 and crosses the y-axis at -1. And so you might suspect that the derivative of this function should be 5. So let's see what we get. Now here we have to be very careful. Just to be very clear, it might help if we write this down. What is the function we're trying to differentiate here? The function we're trying to differentiate is f of x equals 5x minus 1. And so that means that f evaluated at x plus h is equal to 5 times the quantity x plus h minus 1, which becomes 5x plus 5h minus 1. So it might be useful for you to note that. Of course, every one of us likes to write these things out differently. So when I go to the definition, I know that this becomes this difference quotient, and we want to take the limit. And so what we're going to do now is we're going to plug in the respective values. When I plug in this, I get 5x plus 5h minus 1, and then this is minus 5x minus 1. So this is usually the step that most students struggle with, as you guys will recall from earlier homeworks when we asked you to do these difference quotients. So let me annotate this just so it's really clear what I'm doing here. Well, I don't know if it'll be really clear, but it could be helpful. This piece right here is f of x, and this piece right here is f evaluated at x plus h. Now, this sort of looks like a mess, but lots of stuff you're going to notice cancels out. So this is a minus 5x, and that will cancel with this. And the -1 will cancel with the +1. And so once you combine your like terms, you're left with 5h over h. And then now the h's, they are common factors, they disappear. And so you're now taking the limit as 0, or excuse me, limit as h goes to 0 of the number 5, which of course is 5. So what we found then is we have a very sort of useful formula if we ponder it for a little bit. So what's the conclusion? The conclusion is the derivative of 5x minus 1 is just 5. So the derivative of a line, a linear equation, I should say, or excuse me, a linear function, the derivative of a linear function is, in fact, its slope. But that's what we would expect it to be. Does anybody have a comment or a question? Again, think about this. Graph the graph the function y equals 5x minus 1. And ask yourself, how does this function change? If I want to describe it, what describes its change? Well, what describes its change is its slope. That's how steep it is. Look at the previous example. What describes the change? There is no change. It's at the height 4 all the time. So we would expect its change or rate of change to be 0. It doesn't change. If you come back to this f of x equals 5x minus 1, what do we mean when I keep saying change? Well, what happens when x goes from 1 to 2? How much does the output change? What happens when x goes from 5 to 10? How much does the output change? Think about it in that way, in the geometric way. Does anybody have a comment or a question? All right, let's do another one. Let's compute the derivative of x squared now. So just like we did in the previous problem, let's write down what's the function we're working with here. We're working with f of x. That is the squaring function, x squared. And so we want to compute this derivative. So what we need to do is we need to apply the definition. Which is the limit as h goes to 0 of f evaluated at x plus h plus f of x all over h. And now we have to plug in what these creatures are. So let's, oh, excuse me, that's not a plus, this is a minus. So it might be useful up here if we remind ourselves with x plus h, when we plug it into the function, you get x plus h quantity squared, which is x squared plus 2xh plus h squared. So I need to plug these creatures in to my expression. So let's annotate this again like we did the last time. This term right here, this is just the function f of x. These three terms are f evaluated at x plus h. Once again, this step is the one that students just struggle with. I struggled with it 20 years ago. You'll, well, more than that now, geez. You'll struggle with it. It's just what it is. It takes some time to learn. All right, now, once again, just like in the previous problem, this looks frightening, but the x squareds will cancel. And so what you're left with is you're left with the following. And you'll start to notice a pattern when you do a few of these, that after you do your algebra, the only thing that survives are terms that have h's in them. And then, of course, you can rewrite this as 2x plus h if you cancel your common factors. And what's fascinating now, this is the first example. And when you plug in h equals 0, you get 2x. And so, unlike the first two examples, now the derivative is not just a number, but it's a function. And not only that, if we compare our last couple examples, what we're starting to recognize is a pattern. So the derivative of x squared is 2x. Now, what I'd encourage you to think about is the following. Think about the graph of x squared. It is a parabola. And so it should not surprise you then, if you guys remember graphing parabolas before, or even just looking at the graph of this parabola, that its quote unquote steepness or its rate of change will depend on the value x. It's going to be steeper at different points along the curve. It's not a straight line that has the same steepness everywhere. If you draw a parabola, you would imagine that its steepness is going to depend on where you're at along the curve. If you're at the bottom of the curve, you're going to be flat. Now, we did this, if you go back a few lectures, we went to Desmos, and I remember we drew a graph of a parabola, and then I actually put a point on it and moved it around and showed you how the tangent line changed. And so this result that we just calculated is what we should expect if we look at that sort of experiment that we did a few weeks ago. Does anybody have a question about this? As I stare into the camera. As I stare. Okay, so what can we make of these three examples? So let's state some things about these examples that might be worth pointing out. First off, there seems to be a pattern. Now, you might not see it yet, but there's one there. There's actually a few you might recognize. So, and the next thing in the first example, so in 1, there's nothing special about 4. So in fact, the same calculation shows that the derivative of any constant is 0. So if I took that argument we did in 1 and I replaced everywhere I saw a 4, I replaced it with C, where C can represent any number, then we get this result that the derivative of 0. Similarly, in 2, so in example 2, there's nothing special about 5 and -1. So what I mean by that is a similar calculation verifies that the derivative of a linear function, what is a linear function? It's mx plus b, that this is equal to m for any m and b. So what we're telling you is just by doing a few examples, and we're not saying this happens necessarily to you sitting in Calculus 1, but what we're saying is it happens for human beings as a whole, is that when you start doing a bunch of these, you recognize patterns. And then you ask, how do I sort of get to the heart of these patterns? How do I sort of make sense so that I don't have to do all these calculations over and over again? So anybody have a question? Okay, so what do we make of all this, or what's next? So this pattern recognition suggests there are quote unquote shortcuts. when computing some derivatives. Not all, but when we're computing some. So for homework, I'm asking you to do some of these limits, these computations of derivatives using the definition. And the reason I'm asking you to do that is because I want you to have the joy, as we say, of discovering these patterns on your own. The thrill of discovery, as we might argue. So we state these shortcuts as theorems. So what does it mean to be a theorem again? Well, again, a theorem is something that is logically deduced from definitions and axioms. So if you do enough specific examples, you might recognize patterns. And then if you recognize a pattern, you might say, okay, I can logically deduce this pattern is always true. Now, we essentially did that in two simple cases. So on homework number 5, so we ask you to do examples to help you recognize the patterns. I don't need to recognize them. I've done it many, many times before, but we want you to discover these patterns. All right, so once you recognize the patterns, what we can do is we can prove sort of general derivative rules. So let's list some of them, 2 of which we've already proved. So theorem, we usually call this the constant rule. the derivative of any constant is 0. So if C is any real number, the derivative is equal to 0. So that's our first theorem. Our next theorem is the sum difference rule. If I have two functions if I have two functions f and g, and if the derivative of f and the derivative of g exist, then if I want to take their sum or difference, then I differentiate each piece separately. So we saw this when we did our second example with 5x minus 1. We did this. This is essentially what they're saying is we could have done each of those pieces separately. Now, again, these rules, they look sort of cumbersome when they're written like this. They look overwhelming. There's lots of symbols. But you're going to use it over and over again, and you're not really going to think about it. And what I'm asking you to do is to realize that this is not, I mean, we're getting all these shortcuts for free. These rules, these theorems are, the hard work is done in verifying them. And then once they're verified, you get to skip all the hard work and just use simple pattern recognition. So let's look at an example of what I mean by that. Suppose I wanted to compute the derivative of x squared plus 5x minus 1. So we already computed the derivative of each piece of this. We can write this as this by our sum difference rule, and then we know this is 2x, and we know this is 5. this is much simpler than me asking you to use the definition to compute x squared plus 5x minus 1. So if you want a good learning experience, so compare the above calculation with using the definition. What do I mean by that? Well, that would be the limit as h goes to 0 of f evaluated at x plus h minus f of x over h. One is a quick and short pattern recognition. The other would be a monstrous algebra problem with a limit in it. Any questions, comments? All right, so yeah, we'll do one of those in a second, Heather. All right, so the next thing we need to say is another theorem for us. So what color was I using? Doesn't matter. So the next theorem we will state is what's called the constant multiple rule. So this says if df dx exists and c is any number, then if I want to take the derivative of c times my function, it's just c times the derivative. So this might look scary, but if we do a quick example. So suppose instead of differentiating x squared, I had 7x squared. What this rule tells me is that this is 7 times the derivative of x squared. And of course, this is 7 times 2x. And so we would write this as 14x. And hopefully you start to see a pattern here. Now you'll notice that the couple examples I'm using, I keep using x squared because that's one I already have a formula for. Okay, so how do we transition this a little bit to what's coming up next? So a couple things. So the previous examples suggest differentiating polynomials might be easy. And so it turns out they are. So they are once we combine the earlier theorems with what's called the power rule. So the power rule is the pattern that you will start to recognize when you do the homework. And if you haven't recognized it already, it says the following. So if n is a positive integer, so that means it's like 1, 2, 3, 4, 5, 6, 7, whatever, then the derivative of x to the power n is just n times x to the power n minus 1. We've already seen that with x squared. On the homework, you will derive it for for x cubed. So let's just spill out a bunch of these for a second. So the derivative of x is just 1 times x to the 0, which is 1. The derivative of x squared, as we already found, is 2x. The derivative of x cubed, as you guys will verify the long way for homework, is 3x squared. The derivative of x to the 4th is 4x cubed. So there is a very nice, pretty pattern here. So pretty and so simple that it doesn't take a human being to recognize it. We can go to the zoo and train the monkeys to recognize this pattern. Or at least repeat it. So what we can do is we can combine all our theorems, and polynomials are very simple to differentiate. So once we combine all these theorems, which we're calling rules, polynomials are simple. What do I mean by that? Well, let's say we have d dx of 5x to the 3rd minus 2x squared plus 4x plus 7. Well, you just do each piece at a time. This becomes 15x squared minus 4x plus 4, and then we're not going to write the plus 0 there. Does anybody have a question about this? So polynomials, when it comes to differentiating, are very, there's not much going on. You either recognize that and understand the pattern or you don't. You know, you can tell yourself by those theorems, you're just multiplying any constant out front by the exponent, and then you're subtracting one from the exponent. Imagine trying to compute this derivative using the limit. That would be very, very, challenging algebra, to say the least. All right. Good. So let's move to the next type thing. So if polynomials are easy, I know, simple, if you will. So what we want to do is we want to follow the sort of the theme that you guys would follow in an algebra class, pre-calculus type courses. What you did is you first studied polynomials, and then you would study, well, okay, what are the next kinds of functions? Well, you had these rational functions, and you had algebraic functions, and then you built up functions by taking simpler functions and combining them, whether you added and subtracted them, multiplied, divide, composed them. And so what we're at here is we're in a similar place where the opposite seems to be how we might get to the bottom of this. That is if we know how to differentiate all the simple functions, and then we recall that most complicated functions can be built by combining simple functions, then we just might say, okay, great, given a complicated function, maybe computing its derivative just comes down to recognizing how it's built. You know, you have two functions that come together to form a new one, the baby, or, whatever you want to compare it to, like babies have a lot of the same characteristics as their parents, that kind of thing. I don't know, just looking for sort of metaphors or analogies here. But the fact of the matter is, if we know the simple functions, then these theorems, or if we know the derivative of the quote unquote elementary basic functions, then we can use theorems to deduce the derivative of more complex functions. So let's do one of your homework problems. Let's verify the square root rule. That is, we want to verify that the derivative of the square root function is 1 divided by 2 times the square root of x. So once we verify it once, we don't ever have to go through this terrible calculation. We just know the rule. We know the very basic pattern. So let's do it. We have to compute this creature, and we don't have a theorem for it yet, so we're going to have to derive a theorem or a rule. And we remember that this is the definition. Yikes. And then what is the function? Well, the function we're using is the square root function. So when I plug x plus h into the square root, it looks like this. So I need to analyze and compute this limit that has 2 square roots in it. Now, we talked about this a few classes ago. When you have square roots inside a limit, a common trick is to use the conjugate. So what we're going to do is we're going to multiply this thing by 1, but I'm going to write it like this. And then when I do the algebra, when I multiply the numerator and then the denominator, what I can do is I can leave it like this. The numerator becomes x plus h minus, well, we can write it all out. We'll do it once. We'll write it all out. So I'm left with x plus h, the square root of this squared. And then I have plus square root of x times square root of x plus h. And then I minus the same thing. And then it's minus the square root of x quantity squared. And then I'll leave the denominator alone. And so this looks like an atrocity, but what you need to understand right away is that the middle terms add up to 0. So this and this cancel. And then the square root of something squared, they are inverse operations, so they undo each other. And which means the only thing that survives in the numerator is you have x plus h minus x all over this. And so these x's cancel. And then you have h over h, which cancels. So all that survives is the limit as h goes to 0 of 1 over this. And when h goes to 0, this adds up to 1 over 2 root x. And so we have now just verified the formula for problem 1F on homework. This is a brutal calculation. But the good news is, once you verify it, you don't have to go through this calculation again. You now know the simple rule. Does anybody have a question about this? It's a brutal one. But again, now, once we've derived it once, we can now use this formula without having to go back to verifying it. Okay, very good. Now, I'm not going to lie to you. I think, Heather, you were the one that asked. 1E is an algebraic fiasco. So I'll get you started on it. before we do that, here's what we conclude. We conclude that the derivative of the square root of x is equal to this. It's pretty interesting. Here's something else that's interesting, you might think. If we use exponents, we can rewrite. Instead of using square root, what is it in terms of exponents? That is x to the 1/2 power. And what we're telling you is that's equal to 1/2 x to the negative 1/2. So what does this suggest? Well, crazy enough, this suggests the power rule actually works for rational exponents, not just integers. And you'll notice the same thing if you look at D and E. There is a pattern there that suggests that there is a shortcut. We just have to figure out what it is. Okay, so let's get you started on E, because that's an algebraic nightmare that hopefully you suffer through, but most of you will get it wrong a few times because it's nuts. D and E are the same. They just, E becomes much more algebraically ridiculous. Okay, so we want to verify that the derivative of 1 over x squared, another way of writing this though is x to the negative 2 is equal to negative 2x to the negative 3. So that's just, I'm writing it just using negative exponents. And the reason I'm doing that is I want you to see a pattern. So to do this, we note that this is 1 over x to the power 2. And then when we go to our limit, this becomes 1 over, this is x plus h quantity squared minus 1 over x squared all over h. And now becomes the algebra. You need to get this all into one fraction. So downstairs we have an h. What I have upstairs is I have x squared minus x plus h quantity squared all over x squared times x plus h quantity squared. which is terrible. But I can multiply this stuff out, and I can rewrite it. So I'm going to remember my rules about fractions, that I can write the denominator. So I have in the numerator, I have a fraction, and it's divided by h. And so if I multiply by reciprocals, or however you want to think about it, the downstairs becomes h x squared x plus h quantity squared. And then upstairs is x squared minus, now I have to be very careful, this is x squared plus 2xh plus h squared. Yikes. Okay, so if we notice, some things will cancel. This and this go away. And so you're left with this. So what's left is a negative 2x plus h. I'm going to write it like this. So what I'm going to do, I guess I'm running out of space, so I'm taking some liberties with my algebra. So hopefully you fill in the details. So if I factor out an h in the numerator, then it's going to cancel with the one downstairs. And now I'm legally allowed to plug in h equals 0, because that's gone now. The bad guy, the bad factor of h is gone. So what's left is negative 2x minus h over x squared times x plus h quantity squared. And now if I set h equal to 0, I get negative 2x over x to the fourth, which simplifies to negative 2 over x cubed. Yikes, 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 yikes. That was a brutal calculation. So look, one of the beauties of calculus, one of the things that makes it such a fascinating and useful sort of tool, is that it takes lots of complicated calculations and makes them simple. Now you're going to say, well, that was not simple. Well, that calculation was wild, but you technically don't ever have to do it again unless I ask you to do it, which I won't. Well, I'm asking you to do it for homework. But now you have the simple formula. You have the formula now. And so part of me asking you to do this on the homework is so that you get the fact that, yeah, these things are hard. They're complicated, but at the end, there's a reward. You get these very simple patterns. And from these simple patterns, we're going to get to have all kinds of interpretations of these derivatives. As I said, we know we can think of them as rates of change, as velocities, accelerations. We're going to see later this term how they connect with things like geometric things like areas and tangent lines and volumes. There's all kinds of hidden stuff here that is going to be super useful. So what I encourage and hope that you guys will do is you'll take the time to appreciate that. I can't force you to, but I'm hoping you do. Does anybody have a question about this? Now, a common calculus question that you're bound to see on the exam, this week is problems like 3 and 4, where you have to take a derivative and plug a value in, and that gives you the slope of the tangent line at a given point. So does anybody have a question about problems 3 or 4? All right, so here's a standard example. I think I'm out of whiteboard space. What do I do here? Oh, I got an idea. So here's what we'll do. I think I can do this. If I save this whiteboard, and then what I'm going to do is I think if I stop screen sharing, let's see. We're going to see if this works, because they only give me 20 whiteboards. So I have to try something here. So if I stop sharing, okay, we're no longer sharing. Now, really, they won't let me have more whiteboards. All right, I got an idea. I'm gonna have to, here's what we're gonna have to do. We're gonna have to stop this, and then I'm gonna kill this, and then if you wanna do more examples, join back in like 20 seconds. How's that sound? All right, so yeah, that's what we'll do. So I'm gonna end this, and then I'm just gonna start the class right back up in 30 seconds. So you're gonna have to jump back on, and we'll do a couple more examples for you. So if you don't stick around, thank you and good luck on the tests, and I will talk to you guys soon. So hopefully I will see you guys back in a second.